Hi, welcome. Today's lesson is all about the electrons. Now, hopefully you remember some of these facts. Thomson discovered the electrons. Bohr said they had to occupy specific energy levels. And his model also had the electrons revolving around the nucleus like planets revolve around the sun. De Broglie then along and said electrons were not just particles, but they acted as waves and particles. And then Schrodinger took that same idea of waves, but put some mathematics behind it and determined where the electrons would be most of the time, and he described those as electron orbitals. So we want to focus on Schrodinger because that's the modern view of the atom. And so what was that orbital again? What did I say? So remember to take out a piece of paper, pause the video, and write this down. An orbital is a mathematically calculated region of space where you are most likely, about 90% of the time, to find the electron. So what is that in easier terms? An orbital is where you're going to find the electron most of the time. Remember the Wimbledon example from the scientist activities? Hopefully you got to that. Let's take a look at the tennis course. It's made of grass, and used to have these brown regions because the tennis players have kind of killed the grass in this area. So what does the brown regions tell us about tennis players? Well, that tells us where tennis players are most of the time. Not all of the time, but most of the time. So that would be like a tennis player orbital, which would have a shape here and over here. And if this was our nucleus, it would have either side of the nucleus. We would have tennis players. Well, same thing with an electron orbital. It tells us where the electrons are most of the time, the probable region of space that they are going to be in. And there's different types of orbitals, and this is where it gets a little bit more complicated. But we're going to start with a simple one. These are called s orbitals. And S is nice because I can remember it as a sphere. And s orbitals come in sets of one, which doesn't really make sense until we talk about others that come in more than sets of one. And each orbital can hold 2 electrons. So if there's one in a set and each one can hold 2, then you can have a total of 2 electrons. Now be careful. Now this is starting to look like Bohr's model, where the X, Y, and Z intercept would be the nucleus. And here is where my 2 electrons would be. But they're not going around on the edge of this space. They're actually acting like particles and waves in this region of space. Somewhere in this region is where they're most likely to be. Now for the next type of orbital, they're called p orbitals. And they look kind of like dumbbells, I think. There's 2 lobes on either side of an axis, and they come in sets of 3. So here we have one set, here we have one set, here we have one set. So they come in sets of 3, and each of these hold 2 electrons. And they don't hold 2 electrons because they have 2 lobes. Somewhere in this region there is 2 electrons, or can be 2 electrons, and there's not one on this side and one on this side. There can be somewhere in this region of space. If each of these can hold 2 electrons, I can have 2 here, 2 here, and 2 here, so I can get a total of 6 electrons in p orbitals. Now, it's hard to see with this diagram because they're separated. What if we put them on top of each other? What would the p orbitals look like? Well, I have a program that will allow us to do that. So remember to draw this also and write this information down. You can rewind if you need to, but here's a p orbital, the 2 lobes on either side of the nucleus, and 2 electrons can be in this region of space. 2 electrons can be in this region of space, and 2 electrons can be in this region of space. But look carefully what happens when I have them in sets of 3. Wow, together they make of a region of space that is almost, not exactly, but kind of spherical. So when you have 3 p orbitals, you get this spherical region of space. So it's kind of like dividing this up into 3 different regions. So here we have the 3p orbitals together. So make sure you get this information down. P orbitals come in sets of 3. Each can hold 2 electrons. Total, you get 6 electrons. And if you add all the 3 p's together, you get a sphere. So let's go on to the next type of orbital. These are called d orbitals. And if you notice the pattern, s's came in sets of 1, p's came in sets of 3, d's come in sets of 5. And I would draw this example down. This is how I can think of a d orbital. And this can hold 2 electrons somewhere in this region of space. This can hold 2, this can hold 2, this can hold 2, this can hold 2. So together I get 2, 4, 6, 8, 10. I could have a total of 10 electrons in d orbitals. And what do they look like if I put them all together? Because they're not separate. They're all on top of each other, with this being the nucleus in each case, where the x, y, and z intersect. So what happens if I put them all on top of each other? Well, you may have guessed from what you learned from the p orbitals, but here is one d set of orbitals. Here's another. Here's another. Notice this is kind of crazy, right, compared to Bohr's model. And here's another. But what happens if I put them all together? What do you think it's going to make? You're right. It kind of looks like a sphere again. So it's similar to dividing a sphere up into 5 different regions of space. So there we have a d orbital. Did you pause that and get this information? And I would just remember this shape. What about the next set of orbitals? These are called f orbitals. And if you notice, the s's came in sets of 1, p's came in 3s, d's came in 5s, f's come in, you're right, 7s. And each of these, notice how more complicated it gets. Each of these can hold 2 electrons, so 2, 4, 6, 8, 10, 12, 14 electrons can go in here. And notice, instead of having like 4 lobes, notice the S had 1 kind of lobe, the P's had 2 lobes, the D's had 4 lobes, and the F, on some of them, or most of them, have these 8 lobes, 1, 2, 3, 4, 5, 6, 7, and you can't see the last one because it's behind there, but 8 lobes together. And what happens if I put these all superimposed on top of each other like they are in an atom? What do you think happens? Well, let's check that out. So here we have the f orbitals, and they have 1, 2, 3, 4, 5, 6, 7. There's a lobe behind there. 8 lobes for most of them. And here we have another view of that. Here we have another view. We have another. And the last one. And what do you think happens if all of these are combined together? Well, you may have guessed it, but it's still kind of fun to watch. Watch the adding of all these, how they kind of fit together mathematically. And what do you get? Almost a spherical shape when all the f orbitals are together. So once again, it's kind of like dividing this region of space into 7 other regions of space to occupy a set of f orbitals. So we have s orbitals, we have p, we have d, and now we have f orbitals. So how does this compare to Bohr? Well, Bohr was really simple because you drew this nice little diagram and nice little circles. And here we had energy level 1 that could hold 2 electrons. And here we had energy level 2 that we could hold 8 electrons, so 8 little dots. Here we had energy level 3 that could hold 18 electrons. And here we had energy level 4 that could hold 32 electrons. So what about in the modern view? Well, we still have these energy levels, but it gets a lot more complicated. First energy level can have only s orbitals, so that's going to be pretty simple, a sphere. But the second energy level has s and p orbitals, so more complicated. You can put 2 in the s and 6 in the p, so you can still get 8 in the second energy level. What about the third energy level? You have 3 s orbitals, you have 3 p orbitals, and 3 d orbitals. 2 can go in the s, 6 can go in the p, and 10 can go in the d. So 2 and 6, 8, and 10 is 18. 18 electrons still in the third energy level. And what about the fourth energy level? Wow, now you can have s, p, d, and f orbitals. And you have 2, and then 6, and then 10, and then 14. You can have 32 electrons in energy level 4, but a lot more complicated. Next time, we're going to look at what does that really look like if we have all those shapes put together. Well, remember, the S's come out if you add them to be spherical. The P's come out, and it's kind of spherical. Same thing with D's and F's when you put them all together. So watch for next time when we talk about SPDF orbitals and electron configurations. Thanks for listening.